Let's start now with this research presentation. So for the research presentation, Andrea is going to show us first what he is dealing with, like the link between the brain structures and the function, and how the Ising model can help understanding the relationship between the structures of the brain and the function of the brain. So, Andrea, the floor is yours.
Okay, thank you so much. So today I will give you some application of the Ising model in neuroscience, and the main point is really to show how the Ising model, how adaptable is the Ising model, right, to answer the question that you're posing. And so that's mainly the beauty of the Ising model, right? That it's a very simple model and it's very generalizable and it's easy adaptable to your question. So before, let me start, give you a touch of who I am. So you know already that I'm a particle physicist. There's two sounds actually. Yeah. Yes. That's okay. Maybe there is another microphone on. No. That's okay. Doesn't bother me. Okay. So before I start talk about neuroscience, just allow me to give you a small touch of what we do in particle physics and why sometimes looking at things from a different direction can help, okay? And of course, maybe a little bit forcing things, but I just want to show the analogy. So in particle physics, what we do, we mostly accelerate particles in big colliders, and then we make them collide somewhere, and then these particles usually annihilate each other, and they're very energetical particle, and so they can produce much bigger, particle of much bigger mass, okay? And that's, the universe is mostly now, it's cooled down, so it's mostly populated by what we call the first family particles. And in this accelerator, you can build the particles that are heavier of the second and third family, okay? But one point that is very crucial in particle physics is the concept of vacuum, okay? So in fact, in particle physics, the perfect vacuum doesn't exist. Meaning that, so the concept of vacuum, we know what it is. So you're emptying the space. You reduce the number of particles in a vacuum, in a certain volume, and you make the density inside lower and lower, right? And when you say that you get high vacuum, is because your vacuum pump is so good that you can reduce to very low number, the number of particles inside a specific value. Well, what particle physics is telling you that even if in principle you could reach the situation where you have 0 particles in a space at 0 temperature, then in fact, the space is still not empty. So pure emptiness does not exist. And why is that? Because there is this concept of virtual particle and virtual world. So virtual particle are still real, but the virtual world is made of particles that satisfy all the law of physics except the energy momentum conservation. And so just to give you an example, what it's happening is that, let's imagine that you are a pure student and you have $0 in your bank account, but still you're given a credit card. And so then it means that you can spend money to buy things, right? but as long as you don't let people realize that you're buying things. And more expensive are the things you're buying, and then sooner you need to, let's say you buy them, you wear them, let's say you buy an expensive pair of shoes, you wear them for a few seconds and then you bring them back, and then you get back, you get back the money in your account, so that it's still zero, it's not negative. So people don't have to realize that you are using the credit card. And so then more expensive object or merchandise you buy, faster you need to be in bringing them back. Now in particle physics, the same concept. You can have from vacuum the creation of a pair of particles, let's say an electron and a positron. They can just be created from nothing and leave, so there is violation energy, and then get absorbed as long as they are not detected, right? And so if the particle is heavier, let's say you create a quark and an anti-quark that are very heavy, because they're heavier, they need to absorb back quickly. This virtual Bohr exists. It's not just something that it's not real, but it's just not detectable. And so as long as the physics of law are preserved, like for example, conservation of charge, then they are allowed, even if there is violation of energy. Now, why are you telling us this? Well, it happened that in the brain, something very similar is happening to this. So this is the activity recorded intracranially in two regions. One was fusiform gyrus, that is facial responsive, meaning you see faces and that region start being active, start firing. And one region was not facial dependent, right? Now, the main point is that if you look at the firing rate of the two situations, the firing rate recorded by the two electrodes, right? The one that is facial sensitive and the other one is not. The firing rate, it doesn't change too much, right? It's very much consistent between the two. So the point is not the fact that that the firing rate is bigger or smaller, right? From when you have let's say perception that you see a face, but what it brings something to perception, right? Let's say face recognition, respect to your spontaneous activity, is just the timing that the firing rate keep being at a certain level. So in order to have the perception of a face, you need to have the firing rate to be consistently high for a certain time, in a certain time window, right? It's exactly the same what it's happening in the virtual world. Spontaneous activity is the equivalent of the virtual world. There is a lot of things going on. There is a lot of activity going on with a very high fire rate, but it doesn't have the temporal pattern that permits the perception of what is happening, right? So it's like we are not aware of our spontaneous activity. But the point is that in the same way that in the virtual world, the law of physics are there, right? So everything is written in the vacuum, even if we cannot detect it, but it's still written there. And so the idea is similar. In the resting state or spontaneous activity, all the mechanisms of the brain are already written there. Even if we don't perceive our spontaneous activity, but still the mechanisms are there and they follow certain patterns, certain mechanism, right? It's only when you are stimulated or you're involved in a task that then this mechanism becomes reach the level of perception. But all the information is there. And so to study spontaneous activity, right, already permits us to understand the brain because everything is there, right? And so that's what is that was substantially what the people discovered by studying for fMRI, right? Resting state fMRI. Because the way that people were doing fMRI before is just, let's say, stimulating you with visual stimuli and auditory stimuli, and then seeing which are the region of the brain that activated by stimulation of a certain type. Or they were asking you to be involved in a specific task, and they were seeing which are the regions that are involved in that specific task. But the beauty of resting state is that even if you're looking at your spontaneous activity, your brain happened to be organized in the same way as it's organized when you're involved in a task. And so they could find the auditory regions, the visual network, somatosensory network, the DMN, the executive control networks, and so on. So the structure is already in the spontaneous behavior. And so then the idea of models like of the Ising model, or the Kuramoto model, or any other model that try to simulate spontaneous activities, really to identify these patterns that are there, right? Even if you're not stimulated or you're involved in a task. And so this is just to summarize what I was trying to describe with the Ising model, what it's happening, right? So you have so here you have a two-dimensional Ising model. And so this is the situation in which the system is frozen, right? All the spin are up, the temperature is very low. And then when you start increasing the temperature, the system still wants to be highly magnetized, but because there is a little bit of thermal kicks, then certain spins start fluctuating. And then in the situation where the temperature is extremely high, right? Then substantially each spin does whatever it wants. And then there is this critical temperature where the correlation LED explode, in which you have this formation of blobs of coherence behavior that have different dimensionality. And so just to summarize what I explained before, the idea is very simple, right? So you have the system, and you thermalize the system using the Metropolis algorithm. And then once the system is thermalized, you test for flip all the spins, and you can create time courses, right? That's what we went through. And then, of course, once you have the time courses of plus and minus, you can build your correlation matrix. And then if you set the threshold, you can build the graph out of it and so on. And then the idea is that, right, because we have now the connectome, we can take this connectome and plug it in the Ising model, right? And so substantially we have our parcellation scheme, right? And each volt signal in each region is represented by either the by spin can be either up and down, and the connectome gives you the coupling. So this is two models, one by side. So we have a two-dimensional Ising model in which there is only nearest neighbor interaction, right, on the left. And then we have the generalized model in which we have an 84 parcellation scheme, and we introduce the JIJ. And so as you see, the behavior is very similar, right? And so the thermodynamic is very similar. And that's what is happening, right? So what is happening is that in the case of the classical Ising model, in the case of the classical Ising model, right, you have only nearest neighbor interaction. And so when you calculate the correlation matrix, right, you have this diagonal pattern. And so then you can, when you try to fit, right, you try to fit the empirical correlation matrix, the empirical functional connectivity, of course, you can do a little bit better, right? But the pattern that you get, it doesn't make any sense. But then when instead you use the structural connectome, right, and you try to simulate functional connectivity, you find so this what we call T-mean is the temperature that give you the best fit or the minimum distance. And as I was saying before, substantially you find that the temperature give you the best fit is very close to the critical temperature, meaning that at the end, we don't even need a fitting parameter to make our Ising model work, right? So now before we describe what is the dimensionality of the system, right? And so if we have a generalizing model, we need to introduce the concept of distance, right, in order to make it work. And so we know that given two regions in the brain, of course, the Euclidean distance doesn't help, right? Because we know that regions that are far away in the brain can communicate, highly communicate. And so the best way to do it is to introduce a new concept of distance, which is 1 over the number of fibers, or 1 over the coupling. And then what you do, then substantially, you measure the correlation between any two regions versus distance, with distance defined as 1 over Jij. And then you just look at how the correlation decay with distance. And then you can fit these curves, right, with your fitting function, and you can extract both the correlation length and the dimensionality of the system. And so then it happened that with the connectome that we used, it happens that the dimensionality is close to 2. So our brain is flat when it's seen as an Ising model, generalized Ising model. Then you can say, okay, how can we use this concept? Well, a way to use it is in patients that suffer severe brain injury, right? So this is a patient that I like to show because, in fact, has an intact brain. So this is a patient is in a situation of lock-in syndrome. So this patient, they tends to have a brain that is functionally working. It's just that behaviorally, they look like not being responsive. And the fact that they don't look responsive is because their brainstem has a lesion, right, as an infarct, and so their brain is disconnected from the body. But so this is a specific case that is very traumatic, right, because you have a patient that is fully aware and tries to communicate with the world. You can see that the DMN looks very much similar to what you have in healthy subjects, but the patient cannot communicate. In most of the situation, you have instead that patients that do not communicate, they're really because their brain is really affected and can be affected at the structural level or at the functional level. And so in this study, what we did, we compare healthy subjects with patients that suffer severe brain injury with disorder of consciousness. And so this is what it happened in these 25 healthy subjects. So you have the connectome, and then you take the connectome for the subject, you put it in the generalizing model, and then you calculate what is called the susceptibility. Susceptibility is substantially how the magnetization changes with temperature, right? And so the susceptibility peaks at the critical temperature. And so by looking at where the susceptibility peaks, you can extract the critical temperature for the subjects. And this is the average curve with the critical temperature around 0.35. Now, this is what is happening in minimally conscious state patients. Now, minimally conscious state minus and plus. So minimally conscious state patients are patients that, so after coma, you recover the wake-sleep cycle, and these patients show some common following. Or for the MCN minus, it's like just the tracking there. So MCN minus patients are the ones that do not show common following, but they are able to do tracking, right? So for example, you put the mirror in front of their face and you ask to track the mirror, and they can do that. MCS plus patients are patients that instead, for example, you ask them to raise their hands and they are able to do it. So these patients had different etiology. It could be traumatic, it could be cardiac arrest, and so on. And so you can see how the susceptibility is extracted in this case. And this is for patients that VS that are completely unresponsive. Okay. And so now the question that you ask is that, so in these patients, right, the Jij is can be completely affected because the fibers can be destroyed. You may have very strong axonal damage, right? So the Jij that you extract from the TI and then you input in the Ising model can be completely different. And so then the question you ask is that how then inserting a different JJ or a pathological JJ will affect the transition, the phase transition temperature. And so what we see is that in pathological conditions, the critical temperature is higher than in healthy subjects. So this is all the patients together, and this is separately the MCS plus, minus, and vegetative state. And then you can also calculate the dimensionality. And you can see if the dimensionality is different in pathological condition with respect to healthy subjects. And what we found is that the dimensionality is higher. So why the dimensionality of the Ising model is higher in the pathological conditions with respect to healthy subjects? Well, what is happening is that in the patient, when you calculate the correlation versus distance, if the dimensionality is higher, it produces that the correlation decays faster with the distance. So substantially a brain that has lesion, it becomes more higher dimensional because the correlation decays faster with the distance. Okay, and this is also as a counterpart the fact that the critical temperature is also increasing. Okay, so you have higher dimensional system produced by lesion and increase in the critical temperature. Then, as I was telling you, the Ising model, right, even if it's very simple, can still give you some insights. So this is a study that was done completely in a statistical way, so independently of the Ising model. So this is a healthy subject in which anesthesia was, the level of unconsciousness was induced with propofol, okay? And so you have 4 conditions: awake, mild sedation, which the subject is still responsive, is very fuzzy, and then unconsciousness, the subject become completely unresponsive, and the recovery, the subject becomes responsive again. And so the way that we did this analysis, we use independent component analysis, and we extract using template matching the network that you see indicated there, right? But then once the network was identified by looking at the spatial pattern, by doing template matching, we ask if the network was neuronal or not, meaning that we look substantially at the time behavior of the corresponding network, and we ask, is that network neuronal? And what do you mean by neuronal? Neuronal means that the fingerprint that you see there is like of a dove shape. And this is a dimensional space in which we look at spatial entropies, temporal entropy, frequency bands, and then, for example, one-lag autocorrelation, and so on. So different, an 11-dimensional space in which if the components are neuronal, they have this dove shape behavior, okay? Now, what it happened is that when you look at the fingerprint in the different conditions, well, it happened that not all the networks satisfy this condition of being neuronal. And so then you can see that especially when you go in under anesthesia, in the unconscious state, the network may still look like what you expect, but their behavior, which is mostly time dominated, it doesn't look like what expected, what we claim to be neuronal-like, okay? And so then in this statistical analysis, we only kept the network that also satisfy this neuronality condition. And the main point was that when we look at, for example, the DMN, right, the first row, you see that the main finding that was also confirming the previous literature is that in the DMN, the precuneus and the medial prefrontal cortex happen to be disconnected, and the medial prefrontal cortex does not appear in the network anymore. Then you ask, okay, what's going on? So what you can do, given the Ball signal, right, of the regions that belong, to the network, so the Bolt signal, sorry, all over the voxel, you can calculate the average frequency. Okay, so you have the Bolt signal all over the voxel, and you can calculate the average frequency of that specific region, right? You have the power spectrum for the region, so you calculate the average frequency. And then you can see that when you ask what's going on, then the regions that show a behavior of the frequency, in this case, going up and then going down, right? So going up with anesthesia and then back to down with the recovery are the frontal regions, okay? So we use substantially, these are the regions of in the fourth condition. These are the regions of the brain that show behavior in which the frequency increases with the level of anesthesia and then goes back. And at the same time here, what I'm showing is what we call fMRI total, that in a previous work has been correlated very highly with FDG-PET. And fMRI total substantially is nothing else. You run independent component analysis, and then you take all the networks that have neuronal origin, and then you sum them up. You take the absolute value of the Z value of each map, you sum them up, you take the square root, and then you sum them up, and you build one single scalar map out of the spatial patterns. And this one single scalar map overlap very well with the FDG-PET. Okay, so now substantially this frontal region here is the regions that when you have a fMRI total, or equivalently we could say metabolic activity, that tends instead to go down with anesthesia and then it comes back. So what is happening here is that when the fMRI, or let's say the fMRI total or the FDG-PET goes down in a region with anesthesia and then it comes back, equivalently, the frequency of the Bolt signal tends to increase and then it goes back. Okay, so the frequency of the Bolt signal tends to go inversely with the FDG-PET, or what we call in this case the total fMRI. Then what is this telling us? That probably, in fact, the brain could be explained by an Ising model in which we don't have a global temperature, only global temperature, but you have the concept of local temperature. Okay, and why is that? Because substantially what we have, so this is a brain of a pathological state, but this is a VS patients in which, MCS patient in which one hemisphere is metabolically preserved and the other one is completely impaired. And so what we see is that in the regions that have metabolic activity, the Bolt signal tends to oscillate, as we usually know, at low frequency. And in the regions that have depleted metabolic activity, instead the Bolt signal tends to have high frequency. Now, the question there is, what is happening? In the regions that have depleted metabolic activity, we are measuring a high frequency Bolt signal because there is no neuronal activity. And so what we are capturing is just artifacts, meaning the vascular component of the Bolt signal, or because instead in that depleted metabolic regions, the Bolt signal changes in nature and now is more high frequency dominated. So the Ising model is telling you that if for whatever reason, different regions of the brain experience different local temperature, right? Then the frequency of oscillation of the Bolt signal will be different. And in principle, and what we know is that the mean frequency of the Bolt signal tends to increase with the temperature. So now, if a region, so what we can introduce the global temperature that will be our fitting parameter, and the difference in local temperature is dictated, for example, from the scalar map of the FDG-PET, right? So we can say that in region J, the local temperature will be Tj equal to T global times FDG-PET for that specific region at a certain power. And in region I, it will be instead controlled by the metabolic activity in that region I. So now the input for the generalized Ising model will be the JIJ, right, the connector, plus the FDG-PET, the empirical FDG-PET that will control the relative change in local temperature, right? So I will not be able to show you results about FDG-PET, but what we did instead, instead of using FDG-PET as the parameter that control the local temperature, we just use the graph strength. So substantially, in this case, we have the Ising model that was simulated for five regions. So we took different networks, and I will explain why we limited to 5 regions. So we take the five most representative region of DMN, 5 most representative regions of visual network, and so on, right? And so then, meaning that, let's say, focus on the DMN, we have the 5 most representative regions. So we have the JIJ is now a 5x5 matrix. And then we can calculate the graph strength for each of the regions, right? Substantially how that region is connected to all the other. And now the graph strength will be controlling the local temperature in that region, okay? And so now when we fit our model, we just don't use anymore only the temperature, the global temperature, but we have 2 fitting parameters. One is the global temperature, and the other one is parameter alpha that control how substantially the graph strength is modulated, right? And so now you can see, so here we have the network of interest, and this is reported an error measure, right? So how far you are from the empirical correlation matrix, right? And so the column J-pre model is the distance between the structure itself from the empirical functional connectivity. The last column is the distance between the correlation matrix simulated in a random connectome. So you extract random connectome, you simulate the Ising model, and you see how well they will do in fitting your empirical one. And then the post-model is taking the real empirical connectome and putting in the Ising model and fitting the empirical data. And so you see that, for all the components, all the networks, you do always better than just the structural connectome. But at least for certain, like for example, from the auditory network, you can just take a random JIJ and simulate in the Ising model, and we will do even better than just starting from the right connectome. But for most of the network, right, you do, for example, for the singular parietal, when you start from the structural connectome and you input in the Ising model, you get a much smaller error than by just taking a random network, a random JIJ. And on the other side, on the other table, you see the meaning that for certain network, substantially the graph strength wants the temperature to be, give you an inverse relationship with the temperature, and for certain networks, they give you a positive relation, right? A linear relationship. And then you have an idea of how is the change in local temperature for the 5 nodes, right? So then, in principle, what we can do is we can figure it out which all these nodes are and see if the frequency of that node, specifically for the empirical data, corresponds to our model. And here, this gives you an idea of what it will be the simulation, right? So this is the empirical. So you see the functional connectivity empirical, first column, and then you get the best fit, right? By starting from the JJ, and then the functional connectivity starting from a random JJ. Okay. So now the point is that we can add a new extra layer, right? And the point is always the same, that the Ising model is a very simple model and allows you to calculate things relatively simply. And so the extra layer that we want to introduce is to calculate integrated information on our Ising model. So integrated information, as you know, is a theory that have been developed by Giulio Tononi, right, to explain what consciousness is, right? And it's a complicated theory. Substantially, it's telling you that once you have a system, consciousness is generated if the integrated information of the total system is more than the integrated information of the parts, right? And so right now there is a software which is available, which is Python 3.0, Phi 3.0 that is built in Python. And what you need substantially is you need to define what is your system. So in our case, our system is made of 5 nodes, let's say the 5 nodes of the DMN or the 5 nodes of the visual network. So we calculate phi separately, network by network. And then you need to say which are the states in which your system can be, right? And in our case, we have that each nodes can either have -1 or +1, right? So there are a binary situation. And so we know that for 5 nodes, we have 2 up to 5 possible configuration. And so what the phi needs as input to be calculated is substantially the transition probability matrix that is telling you once you are in a specific configuration, right, at time t, what is the probability to go in any other configuration at the time t+1, right? And this is something that we can, of course, build in the Ising model, right? Because given a configuration, we know exactly what is the probability for that configuration to go in any other configuration, right? And so now what is the strategy here? The strategy here is that, so you have an fMRI and you have a DTI data. So from DTI, you extract the connectome. And from fMRI, you can extract the empirical functional connectivity. Then from the connectome, you input in the generalized Ising model, you simulate for the different temperature, and then you pick, by comparing the simulated with the empirical, you pick the temperature, give you the best fit. We call T star, right? And this will be the simulated functional connectivity at T star. So this is the best that our model can do. But now, temperature is fixed, right? Because this is the temperature, T star is the working temperature, meaning our Ising model to replicate the brain needs to work at that temperature, okay? But now what you can do, at the same time, given different temperature, you can calculate integrated information, right? Because for each temperature, you can still calculate integrated information. And what it happens is that, let's suppose that your integrated information profile is like a Gaussian profile, okay? Now, but T is fixed now. And so what you can do, you can look at the T star and see where the T stars sit in your curve profile. So does the T star corresponds to the T that maximizes phi? If this is the case, then it means that consciousness was driving the evolution of that network because the temperature at which substantially your Ising model work to fit the empirical data, something that you know, right? Functional connectivity is the same temperature that is maximizing consciousness. If instead T star is far away from the temperature that maximizes your phi, it means that our brain substantially is working at the temperature, let's say, I say right now, right? Our brain works at a temperature that doesn't maximize phi. So our brain didn't evolve to make our consciousness the highest possible. And then it can be that when we take, let's say, LSD or different hallucinogenous substances, they can bring us to state in which the conscious experience is higher. Because at the end, our brain was not optimized to make consciousness the biggest. Of course, we value very much consciousness, right? Because consciousness, but not necessarily the brain evolved to make consciousness maximized, because maybe it's not needed to adaptation to nature, to our world. And so then we can do that, right? So we can first calculate the specific hits for each network, right? And then we can calculate the criticality, and right, and then we can see, so with this, where the system is critical. And then, of course, we can calculate the T stars, which is the temperature that give us the best fit. And then we can calculate integrated information, phi versus temperature, right? But now, as we were saying, T star is fixed by matching the simulated functional connectivity with the empirical functional connectivity. And so now we can see if the T star is far away from the T that maximize phi, or instead they coincide. And what we saw is that for the dorsal network, we have no statistical difference between the temperature T star that maximize the fitting with functional connectivity, right? And which maximize phi. Meaning that the dorsal network, according to this toy model, is the only network that evolved in the brain to maximize consciousness. And possibly the default network and the retrospinal network, they seem like, okay? But still, there is still significantly different. Meaning that most of the network in our brain did not evolve to maximize integrated information, but they evolved to maximize something else. And so when you take substances that can move you away from T star, right? Then they can produce state of consciousness that are higher than what we experience in a normal situation of an awake brain.
The ventral system is also non-significant.
The ventral system is also very close to being not significantly different, right? Both dorsal and ventral, yeah, and retrosplenial.
When you apply the same to the whole graph, but consider it as and consider each, as community graph and compare with the random graph with the same number of community graphs. Because you did the same for each subgraph, and you compare with the random network.
Yes.
But what happens when you
we
don't consider them separately, but as a community within the same graph, and compare the same graph with the random graph with the same number of community but disposed differently?
Yeah, we didn't do that. And the reason why we did this network by network, of course, it would have been interest to look at the full brain, right? Let's say, but the point is that we are limited from the calculation of integrated information, right? And so already with 5 nodes, the calculation of integrated information is very heavy. And then it just at 10 nodes, it's become impossible, right? And so forget about 84 parcellation scheme.
Because you are using this formula given by Tononi.
Yeah.
But if you come back to what Guillaume Marilec and myself, we calculate like an integration.
Then, yeah, system, you can use that.
The system.
Absolutely.
So in this case, you can consider all the networks
absolutely
at the same time and having this kind of
absolutely. Yeah. That measure or causal density. So you can use different measures, and this is a strategy that you can apply for whatever neurocorrelate of consciousness you have, right? And the strategy is just the same. You just run the Ising model, you fix the temperature by fitting something that you know empirically, like functional connectivity, and then you calculate your integrated information as a function of temperature, and then you see if the T star maximize also your feature or not.
So, because we did this work with Melanie Bolli.
Yeah, I remember it very well.
With this in case of sleep. So you can also look at this integration between network and within network as a measure of the whole organization.
Absolutely.
Of your networks.
Yeah.
And see how this temperature fit with this measure that you can have for the whole brain. But you can also have you can also did the same because you have this integration within each network. So you can have also this measure. You can have both. I mean, the network at the network level
And at the global level.
At the global level, because you have this hierarchy
Yeah.
of the measurement, and this is something that you can calculate easily compared to the proposal of the entropy proposal by Tononi.
Absolutely. So then one point that we are interested is, okay, so we said that the Ising model is statistical model, right? And when we talk about correlation, right? Now we see how correlation, but correlation by definition it's independent of the permutation of the configuration, right? You generate configurations, then you permute them, and you calculate the correlation between two spin, and it doesn't change, right? It's like when you have two time courses, and then you start permuting the time points in both time courses, the correlation doesn't change, right? Meaning that if, for example, I generated the time courses in the Ising model, right, with this artifactual way that I explained to you, and I exchange the present past with future, right, the correlation doesn't change, right? And that's very much reasonable. But what about integrated information that has causality embedded in it, like, for example, grandeur causality? Then if causality is embedded in it, then when you switch the past with the future, you break causality. And so then you want to see if you have this effect, not only in the empirical fMRI data, but also on the simulated data. Because if the Ising model produce time course that do not have causality in it, substantially, so what you are substantially doing with this artifactual way of introducing time is just substantially producing configuration with no causal effect. Then when you permute time points, then you shouldn't see a reduction in phi, right? Because phi is a causal density, is a causal measure. But if you instead, when you permute, you start permuting time points in your simulated data, then the phi that you calculate drops. Then it means that with your model, you were able to capture causality. So there are causal interaction between the spin. And so this is what we did. So we generated time series, right, using the Ising model, network by network, and we calculated the phi. And then we start permuting the time points, and then we calculated phi. And then what we saw is that phi drops dramatically for most of the network when you permute time courses and you rebuild the TPM starting from permuted time courses. Meaning that in the Ising model, you produce causal interaction. Okay? Then let me switch. So far, even in my previous presentation, I never mentioned the external magnetic field, right? So the term that we presented was always the term, the sum over Ij of Jij Si is J. That is the term that we usually use in the Ising model to describe spontaneous activity. But what if you want to simulate stimulated activity? Well, the way to do it, it's very easy, because substantially what you're introducing is a magnetic field, the interaction of the spin with an external magnetic field. And if this external magnetic field has a profile, which is the profile of your stimulation, that substantially this external magnetic field, what does it want to do? It wants to align the spin with the magnetic field. So if the profile is, if the magnetic field is on, then the magnetic field wants to be activated. And when it's down, then the spin do whatever they want, right? So substantially you are able to create, to induce stimulation, but just having a profile that has the profile of your stimulation. And what you need to do is to couple that profile to the regions that are activated by the specific stimulation. And so in this work by Sivaini,
Excuse me.
yeah.
H is the hemodynamic response.
No, H is the external magnetic field.
It's completely the external. So this is something that you have as an input?
You have as an input, yes. And so then in this work by Sivaini Kandipan, so what we did, so again, here there are healthy subjects in 4 conditions induced by propofol, but not only they were anesthetized, but they were also listening to an audio, okay, from taken movie. And so then what we did, we took the taken video, the taken audio, and then we extract features like energy or entropy, different, and these features that, of course, they have a temporal profile, were used as the external magnetic field for our Ising model. And then we use this Ising model with this external magnetic field to simulate the brain under stimulation and under anesthesia. And so you see here the 4 curve that corresponds to the 4 conditions, right? Again, awake, mild sedation, consciousness, and recovery. So this is the magnetization profile. On the upper row is for this Ising model with stimulation, and the lower row is the profile of magnetization in spontaneous activity, okay? And then you can see the energy profile, and then you can see susceptibility that allows you to measure, to extract the critical temperature. And so then, so what we found, so when you have a very complicated profile, right, like an auditory stimulation, usually what people do, they just take the fMRI signal in different subjects and they calculate, so they don't have, let's say, a predictor to predict the activity, and they just use they tend to use intersubject correlation, which substantially you correlate among the subjects the activity, right? And so the regions that have higher intersubject correlation are the regions that tends to do the same things at the same time in different subjects. And so, for example, if there is, let's say, a part of the audios that make everybody startle, then of course that induces some correlation, right? Some common behavior. And so because this was an auditory stimulation, of course, what you expect is that the auditory regions are the regions that tends to be more intersubject correlated. And then there is still, you find some frontal regions that may be due to the engagement, in the common engagement in the movement, under the audio. And then what you see that the intersubject correlation tends to decrease while the subject tends to be more and more sedated, right? So the intersubject correlation can still be seen in the mild sedation and then mostly disappear under unconsciousness, right? When your subject is unconscious and then is get back under recovery, right? And so then what you can do now, you can simulate the Ising model, right? And again, you simulate each subject, and then you calculate inter-subject correlation among the subjects. So these are all simulated data, right? And again, you can calculate, so the last column are the empirical data of inter-subject correlation. And the middle one is the inter-subject correlation for the different condition at the best fit, T star. And the first column instead is at the criticality. And so what you see here is that in order to get an inter-subject correlation that was very much similar to the empirical data, we needed to have a T star. And what it happened, so here it doesn't show, but we needed to go super critical. So we needed to go far away from the critical to the critical temperature. And the criticality, we have in this case that the behavior, our simulation is far away from what you observe empirically. So at criticality, substantially, there is too much induced correlation, which is not what we observed on the empirical data. And then finally, let me give you an example of what you could do to make the Ising model fall asleep, right? So again, in this situation, what do? Well, we use the external magnetic field, right, as the two components that we know in sleep. So in sleep, we know that our wake-sleep cycle is dominated by two components. One is the circadian rhythm, right, the 24-hour circadian rhythm. And the other one is the homeostatic pressure, right, that we accumulate, the fatigue that we accumulate. We start accumulating the moment that we wake up, right? And then the moment that we fall asleep, this homeostatic pressure decays, right? And so substantially, we can model the homeostatic pressure with like an exponential curve, like that you are charging a capacitor, and then the decay, right? The capacitor discharge. And then you have the circadian rhythm. And so then so then again, you have the spontaneous term, and then you have the circadian rhythm, which is simulated by one external magnetic field, and then you have the homeostatic pressure that is simulated by another external magnetic field, and they are coupled to all the cortex in the same way. And then what you can see substantially, you can see here all the networks, and you can see how different networks behave according to the external magnetic field. And so this is just a toy model, right? But so the idea here is that there are networks that substantially are affected because of their JIJ structure. They are affected more strongly by the circadian rhythm and the homeostatic pressure. And instead, there are networks that have more inertia, meaning that their geometry, their wiring doesn't permit them to be very stable. Okay, even if you have the brainstem that is trying to make them sleep, they tend to keep their behavior across the 24-hour cycle. So meaning that depending on the JIJ, the wiring, there are networks that are more affected by the firing of the brainstem that wants them to fall asleep, and other instead that they are more resilient and more robust. So let me just conclude my talk by copying the abstract from this paper from Ruffini and as last author Deco. And so the point that I want to make here is that, so this paper was published in 2023, and it was about the effect of LSD on healthy subjects. And so they claim that in order to explain the behavior of the brain under these hallucinogens, you need to substantially move away from criticality, right? And move away from the TC. So go to higher temperatures, okay? Which, okay, it's very interesting, very interesting, especially our study on integrated information. And so substantially what it says is that when you are under the effect of hallucinogens like LSD, you are moving away from criticality because your functional connectivity pattern changes. And possibly what could happen is that integrated information could get higher, right? Specifically for certain network that do not maximize at the T-star. But so the point is here is that the Ising model is a very simple model, but can really help you answering fundamental questions. So I think I make the point today, and then it will become your friends. Thank you so much.
So thank you very much, Andrea, for this overview of how we can use the Ising model, extension of Ising model to explain the structure, the function, and also to explain the brain, different brain stages, including consciousness and sleep, and probably other kind of diseases that we can also model with this model. Okay. Comment, question? Yes, go ahead.
Questions. So yeah, I think I have two questions. So the first one is about consciousness, like you said. So so my understanding is that consciousness is in terms of Ising model, it's a configuration with high energy, right? Or, I mean, it's integration, and integration in the Ising model corresponds also to some configuration with some reasonably high energy, right?
Not necessarily.
Okay.
So here you see so this is the integrated information, right? And you see that as for most of the network as a bell-shaped profile.
Yeah.
Okay. Meaning that there is a temperature at which phi will maximize, and then it will decay back.
Okay, but that's for the separate subnetworks.
For the separate subnetworks, yes.
Not for the global network.
For the global networks, we just cannot calculate.
Okay. So okay, so the integration here. So the integration only concerns the subnetwork.
This just 5 nodes. So you're measuring how these 5 nodes, how the information is generated at this 5 nodes level, and now this information is integrated.
Oh, okay. So do you think, because you said that the brain doesn't seem to have been made to maximize consciousness.
Yeah.
So do you think that the reason, I mean, one of the reason is to allow subnetwork that are responsible for the or vital functions to function correctly? So I mean, if the consciousness was too high.
I think it's the way that the brain evolved is just to make you survive in a very uncomfortable environment, and to be conscious of what's going on is just not really needed at all the network level, right? And then you just want to be as responsive, right? So there is a lot of behavior that is dominated by just being quick the moment that something, a threat is happening.
Yeah.
And so that's what I think mostly dominated the evolution of our brain. And then consciousness happen as a side effect, and then we value it a lot, right? But it's not that important.
Okay. So my second question is a bit probably outside the scope of your talk, but because I recently followed, I read about the controversy
Yeah.
that was brought about IIT right
Yeah.
now. So I would be interested in hearing your
Yeah, so I'm
opinion
glad you
about this.
asked because I have a very strong opinion.
Mm.
And I would have not tell without being asked, but because you asked, then I can say. And so I think that what it happened was very bad for consciousness because these scientists, and there are 3 colleagues at Western, they use the scientific authority to claim that something is pseudoscience.
Yeah.
They have all the instruments. Nobody's selling that integrated information is the right theory. Most probably it's not. It's just an attempt.
Yeah.
And as it's also a good attempt because it permits people like me to implement it in a model, right? The global workspace theory, I don't know how to implement it. Granger causality, I know. Your model, I know. But other theory, not. But the point is that, so integrated information theory can be fought, can be, right, challenged in the classical scientific approach. So people go to conferences, they have debates, discussion. If you send a peer review, if you send a paper on a journal with integrated information, there will be reviewers that have the expertise and so on.
Yeah.
So I think what they did, it was not.
Yeah,
super.
I mean, most of them are not experts of IIT.
Independently of that, just all the model on consciousness right now have the same issues, right? Of course, there are some. You are mathematicians, right? So as a mathematicians, you know that you make assumption, and then rigorously you derive everything from that assumption, right?
Yeah.
But so you have awareness of the assumption you did, right? And so people has awareness of the assumption that have been made in integrated information theory. You may not agree with that, but then after these assumptions are made, there is a rigorous procedure to calculate whatever they think it's fit, right? So that's it. There is nothing more than that. So I think was very off what they did, and it will not be good for science and consciousness.
Thank you very much.
Thank you very much for your nice presentation. What is the most important cost of the simplicity of the model? I mean, what is the most important limitation of this model?
I think the most important limitation comes from when you try to introduce time, when you try to make the system dynamical. And I think we are all following Freiman et al., but I think we can do better than that, or at least try different other ways to introduce time in the model. That's, I think, is one of the biggest limitations. And then, of course, it just have one single parameter, right? So then it's clear that when you compare the neural mass model, how the neural mass model perform in fitting functional connectivity, it will do better than the Ising model. But the point is that, we are using only one parameter.
Okay, thank you. I'm going to ask you a question on that. I was thinking about the last question. First question, a lot is based on the critical topology, DC, which is an important feature.
Yeah.
Okay. But let me back to this depends on GIG, I mean the connectivity.
Yeah.
Okay?
Yeah.
And we know in the case of MRI, the fusion MRI, that the truth corresponding to this connectivity, we know that we have like a suboptimal connectivity that we can extract from the diffusion imaging due to this confounds that we can have in within the brain. So how this information or less information that we have on this anatomical connectivity can affect these important features, is the critical temperature.
Yeah, so the critical temperature depends only on the JJ, right? And then the point is that if you just let the JJ predict the FMR, let's say the Bolt signal, then you cannot do a super good job. Meaning that the JJ plus the model still don't do enough well in predicting functional connectivity. And that's why I think it's important to make the model evolve by introducing the concept of local temperature, and then introduce inputs, extra inputs like FDG-PET or whatever, to help the model better fit. And so again, there will be only one fitting parameter, because there is still, the T global will still be the only fitting parameter, but instead of having only the JJ as input, there will be an extra input that will come, for example, from metabolic activity, right? Let's say in this example, right? So let's look at this image, right? So if the damage in this patient is not axonal at all, okay? Maybe there may be axonal, but let's say that it's just metabolic, purely metabolic, right? Meaning that it's just the gray matter that is suffering. So when you calculate, when you do the JJ, when you do DTI, measure DTI, and you extract the tractography, you still get the connectome that is very much the same, right? But then you look at functional connectivity, and functional connectivity in this kind of patient, for example, will have only the DMN in one hemisphere. That is the hemisphere that has metabolic activity. So how can you then use the Ising model to predict the functional connectivity in which there is only one hemisphere working, when instead the connectome will tell you that functional connectivity should be good anyway? And the only way to do it is first by having the input from FDG there in such a way that substantially you have an extra layer information. They will tell you, look, even if these regions are well connected as supposed to, but because they are metabolically depleted, then the temperature, the local temperature will be much higher, and the functional connectivity will be lost.
Okay, but still, for the anatomical connectivity, this is not optimal at all. I mean, we know that.
Oh, yes. Well, we need to do a better job.
Yes. So have you tried simply to do some kind of simulation?
Yes.
Having some kind of attack on this.
Yeah. So
see how this.
Yeah. So what we did, we extract the connectome in different modalities. Like, for example, there was this debate: is the probabilistic approach or the deterministic approach do better? And so what we found is that when we calculate the probabilistic connectome, which is not very sparse, right? And we calculate deterministic connectome, we input in the Ising model, the deterministic does a better job than the probabilistic in predicting functional connectivity. So my suggestion is that if you want to predict functional connectivity, use the deterministic approach in your model, the deterministic IJIJ.
So what is the idea behind this comparative that you link to the FDG?
Yeah, the main idea is that we really observe in, let's say in patients, we really observe that when the Bolt signal tends to have different frequency of oscillation, the empirical Bolt signal tends to have different frequency of oscillation in regions that have different metabolic. And so in this patient, if you calculate if you take the Bolt signal in a region that is metabolically depleted, there the Bolt signal will tend to oscillate much faster.
I remember year before you come to Paris, linking between fMRI and the resting state and the FDG.
Yeah.
What is the end of this work that you did?
The end of this work is that it's the end. It's this one, right? So people, there are other people that did similar things. And so to me, it could use fMRI to estimate the FDG-PET could be a good estimate. So my point is that if you don't have an FDG-PET machine in your hospital, you can still use resting state fMRI and combine the ICA in this way to get a good estimate of what it will be your metabolic activity.
So
but
in this case, I'm back to your model. Rather than using FDG, you use fMRI. So you still stay within one modality, and you have another modality that you can introduce to change the temperature, as you mentioned. Is that something?
Yeah. So what I want to do is to use to take fMRI, and so suppose that I cannot have FDG-PET, right? Yeah. So I will take fMRI. I will calculate fMRI total, which is the simulation of FDG-PET, and I will use this fMRI total as my FDG-PET to put in the Ising model. That's right. And then I will do this and see if my model works better. Yeah.
Okay. So let me know when you think this experiment. In the estimation, you have some alpha coefficient who are positive, other are negative.
Yeah.
Okay. Can you give me some interpretation of what alpha negative means?
Well, alpha negative, in fact, I wanted them to be all negative. That's what my prediction, right? Because I think that bigger graph strength also usually regions that have bigger number of connection, usually they are also the regions that are more metabolically active, right? And so then from here, I would expect that the temperature always goes like graph strength up to minus something, right? That there is 1 over the graph strength. So the positive, I don't know. I still need to think about it. To me, it makes sense to have a negative exponent, and the positive exponent, I just at the moment I cannot make too much sense of it.
My last comment, general comment, is about what you mentioned about confuseness, and so predict is the dorsal and ventral system, which seems like linked to this property of the brain. But other experiments done in different groups look at the frontoparietal areas. When you did the experiments with stimuli, perceptive stimuli and non-perceptive stimuli, it can be sound, it can be visual stimuli. So what we see from the activity point of view using fMRI is that this frontoparietal cortex is linked or not, depending on the fact that you are aware about the stimuli or not. Okay, this is the experiment that few people did, and that from this kind of experiment, we go with this global workspace and developing this theory about consciousness. So that's one way, but the target is the frontotemporal network. In another side, you mentioned the work of Tononi, who did this work with the sleep at stage 3 and 4, and look at the connectivity, and mentioned that this connectivity is broken at this at stage 3 and 4 using EEG. This is with Massimini. And he said, okay, consciousness is a property of the brain, and we can measure this consciousness by the this large-scale communication between area of the brain. So connectivity becomes like the way to catch
Yeah.
this conscious or unconscious environment of the brain. Still, this is not contradictory about the frontoparietal area, because this is exactly in the frontoparietal area we see that we don't connect between the frontal area and the parietal area with the stimuli that people do. So, what is behind this ventral and dorsal network? Maybe you're right, but you are mentioning something completely different from what most people mention.
Yeah, I think that I think what our findings are a little bit more congruent with the approach of Tononi, that they claim that is mostly a parietal that parietal region are more relevant for integrating information other than the frontal part. And but so at this point, the only things that I can say is just that the wiring of the specific network, right, is what control the behavior of the network. And then our findings are mostly detecting the different wiring produce different profile for the integrated information, and that's mostly it. So it's difficult for me at this stage to say more than that.
So just to mention my last lectures on consciousness, and I find this is speculation, but interesting. A few very strong mathematicians meet with the psychologists, and they move through how we can model the consciousness, and it comes with tools, and the tools in mathematics called topos. I don't know if you know this kind of theory of Grothendieck, and so Grothendieck is for me, it's probably one of the more genius mathematicians that I know. Probably more than all Hilbert and others. I really think he's the greatest. So yes, it's yeah. I don't know how his brain works, but it's something. For me, it's really genius. So he formalized things completely in theoretical way, without any kind of, view of application. But I see other mathematicians coming saying, "Oh, these tools that he called topos, who comes from the theory of the category and the algebraic topology and all of this is very interesting to catch this information about the consciousness." I have not understood very well completely this link, but I would like to connect it to what we know about what Tononi mentioned, other people, the global
workspace
and so on. So making a link between all of this, but this is just as an information, who seems to me maybe very interesting for the future, because it links between all what we try to do. Connectivity is also geometry. So having, properties of this network geometry, this is completely something that we can catch with what we call the topos. So maybe there is a thing. So, but I at this stage I don't know. Okay, this is just a general comment. Any final comment?
Maybe a very short question, like, is there any code available to track and model?
Yeah, so just send an email to Dylan Jan, right? And he will share with you the Python of our code. And it can you input the JIJ, and it will calculate all the thermodynamics property and simulate time courses and calculate the correlation.
Thank you.
No problem.
So thank you very much.
Thanks a lot.